All right, what we're going to add today is we're continuing on our reactions moles combination. Reaction moles combination is called stoichiometry. It's written at the top of the page, so you don't need to remember how to spell it. We are going to work today with the concentrations of solutions. So we're going to do molarity concentrations with reactions. So we're going to pull up that molarity chunk that we did in the mole unit and add it to our reactions that we have done. So remembering the formulas that we did before, thankfully, look what I did for you guys. I gave you this formula, which is the definition, and the two rearrangements of the same formula. That's three versions of the exact same formula. It's not three formulas. It's three of the same one formula. Now, reminder is do not use 22.4 liters per mole. That is only true for gases at STP. It's not true for solutions. If you got water, that's absolutely not true. So for us today, there's not too much like new theory. It's just going to be new applications of using molarity with the stuff we learned already this chapter through lessons 1 and 2. So we're going to bring in all our balancing reactions knowledge to all of our mole calculation knowledge and put them together. So my first example page is only one reaction. So the first reaction is an antacid, calcium carbonate, and hydrochloric acid. It has a neutralization reaction, which also produces carbon dioxide. And so this particular reaction, the first thing we need to do is balance this equation. Is this equation balanced as it stands? No, it's not balanced. Which element needs balancing? The chloride first, right? So I looked and saw 1 chlorine here, 2 chlorines here. That's bad. So I should put a 2 over here. Start with that. Oh, thank you. I'm writing all this stuff down and no one's seeing anything. Thank you. There we go. Now you can see the stuff written down. Yeah, because freezing only does that, doesn't do this. What we're doing. Yeah. So that fixed. My hydrogen is now 2'd. I got 3 oxygens here. How many do I have over here? 3. I got 2 here and 3. So this is finished as of now. So we have now officially balanced this. And when we look and say we balanced it, we go 1, 1, 1, 1. So it's a very simple as far as the balancing goes. But you always have to double check to make sure it's balanced first before we go and do anything else. So now we can do our conversion fractions adding together. So we're taking a tablet of Tums, has calcium carbonate, a mass of 0.75 grams. It's a little bit of the calcium carbonate in the little tablet there. How much stomach acid can you neutralize if your stomach acid has 0.01 molar? Your stomach acid is significantly stronger than that, but you can fix this much of it based on this particular example. So you're going to fix this much of it. You change its concentration by this much because your stomach is around 1, roughly. It's reasonably strong. Okay. We'll start with getting our mass and molar thing. So we got to go from the mass we're given. We got to turn that into a moles, turn that moles into a volume, and then turn that volume into a concentration. So we got a lot of steps in this particular example. But first what we're going to do is we see this lovely mass here, and we know it's calcium carbonate. If we have a mass, we need a molar mass. So first step is the calcium chloride, calcium carbonate, I'll say it properly. Calcium carbonate slowly, molar mass. So molar mass, not uppercase A, ACO3. So we got 1 calcium, 0.1. Slide this up now that you guys can see all this. There we go. 1 carbon, 1 12.0, and 3 oxygens, 16.0. So that's our molar mass little side calculation. We're going to start with that. It's always a good idea for us during these lessons to have your periodic table beside you and a calculator trying these while we go. It's the best way to feel confident that you can do it and not, this is a mystery and I can't do it. I think it's about 100. So it should be 100.1 grams per mole. That's my calcium carbonate. Do we agree? Those of you that have tried it, good. Always a good idea to try that. So I've got a molar mass, so I can find out how many moles I have. All right, let's do that. 0.750 grams of calcium carbonate multiplied by my molar mass. 100.1 grams for every 1 mole calcium carbonate. Now, remembering in this chapter, we have to tell which one we're measuring. It's not just moles and grams. We have to tell us of what kind. What kind of compound do we want to measure? We want to get HCl and its volume. So we got to get from calcium carbonate into HCl. So we have to do a mole ratio. So we have calcium carbonate, and it's 1 mole of calcium carbonate. If I have a mole of calcium carbonate, how many moles of the HCl should I have? Where'd the 2 come from? It's the balanced reaction. It's up over here. That's where the 2 comes from. Right. Put the 2 there. So it's a 2. And that 2 comes from here, right? That's the 2 there. So if you're following along, that's where the 2 comes from. Just make a big mess of this particular set of notes. But we want it very clear where this is coming from. Okay, so this will give me how many moles of HCl. So we'll do that. So we'll put this in our calculator and get this out. Because we need to... Also, I'm out of page, so I'll finish this line and then continue on with the next step lower. This one will give me a little bit. Should be pretty little. Ooh, very little. 0.014985 moles. Obviously, that's way too many digits, but I'm not finished yet. So keeping extra is always a good idea. But as far as your calculator is concerned, you should just leave it in your calculator. Don't hit clear until we're done our next step. Which of these formulas at the very, very top of the page should I use? 1, 2, or 3 for us to solve this question? Yes, this should be the third one because we want the volume equation. So I know I want volume is equal to the number of moles divided by the concentration of the solution. Do I know both of those numbers now? Yes, I do. Number of moles is what I just found. So the number of moles I have here, 0.014985. But you're not retyping that into your calculator because you totally have it saved and have not hit clear. Moles over 0.0100 is the molarity. Oops, I don't want to write it like that. What's a different way of saying molarity? Yeah, it's moles per liter. And so when I do this division, I will actually get a liters measurement out of this particular question. When I do this division, I'm going to get 1.4985. That's a lot of decimals. How many should I keep? 3, I think. 3 is the right number of sig figs anyways. 3 sig figs. So that's going to end up being, oh, lovely, 1.50, I think it's going to have to round to. Yeah, it's 3 significant digits here, so 1.50 liters of HCl. Oops, that's not how you do HCl. Lowercase l. So now we have our final answer, and we always want to make sure we're writing our final answer with the units we have, with what chemical I'm measuring, and the right number of sig figs. All right, let's try our next one. I'm going to put it right at the top of the page so we can see it. Everything else is written below. The reaction, the balanced reaction is the same as it is at the top of the page. So we could just start our plan before. What volume of carbon dioxide gas at STP is produced if I have 120 or 1.24 liters of this much acid reacting with a whole bunch of calcium carbonate. Okay, so I'm going to write this one out like we did before in our old chapter. We're going to write our little plan arrows here because I think it's worth doing here in this part of the equation. So the plan here is we're going to use the concentration and volume of the HCl to make moles HCl. So once I get moles of HCl, anytime I get moles of anything, I can turn it into moles of anything else in the reaction. I can turn it to anything else that's in the reaction. And so we're going to turn those into the moles of CO2. And once I have moles of CO2, I can go into volume CO2. I can use the STP to get the end volume. So this is the STP part. Great. Questions about the plan? Does that feel like we can accomplish this? So we could do it all in one, but I think it's easier to do in two. So we're going to do it in two lines. I think it makes more sense to do basically like this chunk. Oops, pen's on my screen. That chunk first, and then the second chunk second. So we're going to do it in two lines like we did before, because the fractions sometimes are weird. All right, which of the three formulas do I want to use to get moles of HCl out? There's three formulas at the top of the page. Which ones do I want to use? Very talkative group. The second one. It's the N equals C multiplied by the volume. And so this is going to lead me to the concentration given, 0.0055. Yep. And that's moles per liter multiplied by 1.24 liters. So this is a reasonably straightforward multiplication question, and this will give me moles. It's a very, very small number, 0.00682, I believe. And that's going to give me moles of HCl. So that's going to give me the number of moles in this particular reaction. And now I will do my multiplication by my mole ratio to get my carbon dioxide stuff. Yes, that is to the -3. So it depends on the way you're setting your calculators. Some calculators start giving you zeros, some start giving you scientific notation at this size. It is correct. So that is the -3 scale. So we're going to rewrite the number just because that's how the math has to work here. 8.2 moles HCl, and because I'm just trying to describe all my thoughts here. So then I know the mole ratio for the HCl is actually a 2 from the balanced reaction. And it's a 1 for the carbon dioxide term. So the carbon dioxide term has a 1, and the hydrochloric acid term has the 2. And then we will get to the STP part of the equation, 22.4 liters for every 1 mole of CO2. And our final answer here will give me a number of liters. I think I can get away with rounding it right now. What's the number of significant digits I should keep? Don't move their hands, guys. It's 2. So 2 from this guy up here. So it should just be 0.076 liters of CO2. And that should be the end of my question. I've got the right number of significant digits. I have a volume of gas, and I said which gas. So I've covered all the bases here. Is that not it? Do you disagree with me? All right. This is useful for a very, very special process that is very common in chemistry. It's a very analytical process. Hopefully we'll get to do one if I can set it up. The plan is to get one. Hopefully it doesn't get timed out. This is called a titration. Oops, I don't want it in red. I want a titration. Yeah, I'll get this spelling it when I figured out how this iPad works. It's only been 4 years. Titration. Now, it's used to find the concentration of unknown solutions. When we mix these two together, we get what's called an equivalence point. When the ratio of moles in each compound, the solution reaches the ratio of moles in the balanced reaction. So at this point in the reaction, we get the mole ratio that's actually in the solution is the one that matches the balanced reaction. And therefore, you get a tipping point. And usually what we do specifically in a titration is we add some kind of indicator. And so the indicator will switch colors. And so you're looking at a solution, change color, and that tells you you've reached your equivalence point. And then you can take measurements and figure out what happened. So the basics of the titration is that your balanced reaction becomes the reality of the situation, and so you can do the matching of each. Sometimes it's called fancy the stoichiometric point, which is, I'll try to spell here, stoichiometric point. So it's a stoichiometric point because sometimes it's not equivalent. Sometimes your mole ratios aren't 1-to-1. They're 1-to-2. So equivalence doesn't make sense because it's not equivalent. It's 2-to-1. Stoichiometric makes sense because it's at whatever ratio the reaction tells us it should be. Yes? Next reaction. So when sulfuric acid reacts with... I didn't order one today. Back to the lesson. What are we doing? Who am I? Sulfuric acid. What's the formula for sulfuric acid? It's H2SO4. We know what sulfuric acid's formula is. What is sodium hydroxide's formula? What's sodium? It's Na. O with an H. So it's sodium with the hydroxide ion. No numbers underneath because sodium's a +1 ion, hydroxide a -1 ion. They are equivalent. So reacting these two things together, what happens when we do a neutralization reaction? What do we get out of a neutralization reaction? You get water. Good. Let's start with water, H2O. What else are we going to get out of this particular example? Almost. So we know we're going to get sodium, and we're going to get, SO4, a sulfate ion. What charges do these each have? What's the charge on a sodium ion? A 1, right? What's the charge on a sulfate ion? No. 2. So I need 2 sodiums for every sulfate. Notice the balancing here, the H2 here, the Na2 there. Those are going to match. So now that we've got our formulas correct, we have to balance this. So where do I need to throw extra numbers? This isn't balanced as it sets, right? Where do I need more? Let's add some sodium here. Does that fix everything? No, what have I messed up here? Need 2 waters too because it's messed up the number of oxygens. So remember the best strategy is to take sulfate as a singular set, and I don't count all the oxygens in the sulfate. 1 sulfate on the left, 1 sulfate on the right. And there I'm just trying to count these oxygens with those oxygens. Those are what I'm trying to balance. So 2 oxygens here, 2 oxygens here, good. And now I have 2 hydrogens and 2 hydrogens, which makes 4. These 4, we're done. And so put 1s on the ends. You don't have to put the 1s. It's not wrong to have them. I like to do it because it shows I've finished. And so it's easier to do the mole ratios in the fractions when you put the 1s on there. It just makes life more complete. But just like I don't have to put the 1 at the sodium here, I know there's 1 sodium in that formula. Okay, So when I've done the moles of sulfuric acid to sodium hydroxide, what's the mole ratio? Sulfuric acid to sodium hydroxide. Sulfuric acid, what's the number in front of sulfuric acid? 1. What's this number in front of sodium hydroxide? 2. So I need to have, when I'm mixing this evenly, to balance this reaction, 2 sodium hydroxides for every sulfuric acid. So if they have the same concentration, I know I will need twice the volume of sodium hydroxide that I do sulfuric acid. This also works out if I have the same volume of each, I need twice the strength of sodium hydroxide, twice the concentration. So I know that at the equivalence point, I'm going to have a ratio of 2 to 1. So when this thing is perfectly neutral, which means I have nothing but water and this sodium salt, I know that there will be twice as many moles of the hydroxide as there will be of this sulfuric acid. That's kind of the idea of the stoichiometric point, or the equivalence point, is that when it is balanced, we have this ratio. If you just start dumping things into different things, you're going to have too much of something. That's a later lesson there. How much extra we calculate, that's a different lesson. But for now, we're looking at when is it perfect. So let's do a very easy one, and look how much space I gave you to do the math on it. Let's see if we can figure this out. So if I have 0.2 moles of sulfuric acid, how many moles of hydroxide do I have? So if I have 0.20 moles of sulfuric acid, how many moles of sodium hydroxide should I have? 4. 4. Why 4? Because it's 2 to 1. So I need twice as much. So it's going to be 0.40 moles. Twice as much. So here we have 1 of those, 2 of those. That's the idea. All right. So we're going to do a different titration. So we still have our acid and we still have our base, but we're going to have a different balance. So let's try balancing this reaction first. So first step I want you guys to try, balance it. So take a second, try to put the numbers where they belong. We're balancing this. Okay, so now that we've balanced it appropriately, that's what I think I got, we can do the math steps. So we're going to take 19.8 milliliters of the acid with an unknown concentration, and we're going to react it with exactly 25 milliliters of the 0.5 molar potassium hydroxide. What is the molarity, or specifically concentration, of the acid? So what we're going to do is we're going to figure out our concentration and volume of the potassium hydroxide. So what we're going to do first is we're going to take this set and make moles, right? Because moles is how we go back and forth. So we're going to turn those two numbers into moles. And then we can do the mole ratio and then go back and find concentration. So first step is this part. We're going to find moles of the potassium hydroxide. Keep trying to say KOH, but it's potassium hydroxide. All right. So first step, we're going to do find the moles. So that's N. So we're doing the math for N. N is equal to C times V. Almost got that backwards. So C times V is my concentration. What's the concentration of this particular compound? It is 0.500 moles per liter. We're going to multiply it by, now we're not going to multiply it by 25, are we? Why? Because we need it to be in liters. We got to do the division, so we got to do this 0.25. 5, and how many zeros? 1 0. Liters. So we got to turn it into liters. So 25 milliliters into liters, and now we can do our math step. Let me just do it. Might as well do it live. I'll do it this way. 0.5 times what am I doing a calculator for? 0.0125 moles. I didn't need a calculator for that. Okay. So before I go past this, we're going to do one more math here. This is moles of the KOH, right? And I want to get moles of the phosphoric acid. How much do I need to do here? Do I need the same amount of moles? Twice as many moles? Half the number of moles. So we're going to multiply this by 2 mole KOH, and 1 mole H3PO4. Yeah, I got that right. So now we're going to get a number, half of that again. So now we have 0.00625 moles, in this case, of the acid, H3PO4. So now that's how many moles of the acid we have. Because this is the amount of moles that would be in balance. Moles of the hydroxide was 0.125, and so we cut that in half to find the moles of the acid. Right, just looking at this 2-to-1 ratio right here, and so I need to have half as many of those as I do of those. So now I can take this many moles, I can divide it by the number of liters, right? So we can get a concentration. So the number of liters we used, which was 0.0198 liters of the solution, H3PO4. So that's how many liters of it I used. And then we can get our math done here. And this will give us our moles per liter concentration. 0.00625 divided by 0.0198. 0.31. Okay, so here we get 0.315656. Oh, a lot of 5 6s. Looks like it's going to repeat a lot. How many significant digits should I include in this question? 3 looks good. So 3 is going to give me, going to round up. So at the end, 0.316 molarity. And it's molarity of the H3PO4, phosphoric acid. That was a lot. Please ask me questions. All right, let's do the last one. Same setup. Same idea. We're going to look for what we have both of and start with that one. So that one we have both of, so we're going to get the moles of that one. Moles is always the goal. If we have like, I don't know, find moles. It's always a good idea. Find the moles of something. Because if you have moles, then you can go through the reaction. I can pick out any other piece of the chemical reaction if I have the number of moles. So how do I turn these two numbers into moles? That's the same as it was above here. So the number of moles is equal to the concentration times the volume. Concentration in this case is 0.25 moles per liter. And I got to multiply it by, again, transforming it into liters. Oops. 25 liters of the substance. So then I'm going to get 0.25 times 0.125, 0.03. Yeah. 0.0125. Oops. I did that wrong. Let's undo that one. Slide back down. We got to do 0.3125 moles. All right. What am I going to try to get it into? Which one am I looking for? Right, but I got to turn it into what chemical? I have moles of acid here, PO4. So that's what I have. I have currently moles of acid. What am I going to have to multiply this by? Nothing. Why nothing? Oh, why would I multiply it by 1? I have to do a mole ratio, right? What's the mole ratio? I need to have H3. I'm going to run off a page here, but hopefully you guys are right better than me because I can just cheat and add more page. So I'm going to try that again. Oops. Ugh. Page back on. Okay, so I have 1 mole H3PO4. How many moles of what is it that I'm looking to find?
KOH.
The KOH. So let's do the KOH here. Every time I say KOH, I think of the KOA campgrounds. So what's the number in front of the KOH in the reaction? It's a 2. So we put the 2 here. So we're actually going to be multiplying this number by 2 to get our number over on the other side. So we'll take the number here and double it. So 0.0625. So let's see if I can keep all this on the screen. Almost. There it goes. On the screen at least. So on the screen, 0.0625. And that's going to be mole KOH. We're going to divide that by how many liters? No. Oops. I want to find liters. Am I doing this wrong? There we go. Moles divided by moles per liter of the KOH. Almost did that backwards. Moles divided by moles per liter is good. Then we get 0.200. There we go. From this piece here. That seems good. Divide by 0.2. There we go. That's going to be liters. Do I have the right number of significant digits right now? No. How many should it be?
3.
Should be 3. So I got to round it to here. So I got to use 3 significant digits, which is going to make that last number go up. So at the end, 0.313 liters of the potassium hydroxide was needed. So the goal here is if I have 125 liters, or like more, hopefully, more simply, it's 313 milliliters. Would make more sense if I was actually pouring it. But so I'm going to need 313 milliliters of the hydroxide to make 125 milliliters of the acid balance. Now, those would be exactly the same. If the concentration was the same, the concentration is not the same. They're a little different, so it's nearly the same. Words.